Greetings, mathophiles. Welcome to a video on one of the core concepts in all of calculus, which is that of the derivative. You're going to get the most out of this discussion if you know a little something already about instantaneous rates of change of functions at fixed values of the input variable. There's a video that we have on this channel, and I'll put a link in the description that will give you some background on that. But to briefly recap before we continue, the idea behind an instantaneous rate of change is that you take a look at an average rate of change over a shorter and shorter and shorter interval containing the value of interest of the independent variable. And ultimately, we formalize that in terms of a limit. We also defined the slope of the tangent line to be equivalent to that same value. And graphically, the notion is that we're looking at the slope of a secant line as the 2 points in question get closer and closer and closer together. The example we'll be using throughout this video is the function f of x equals x squared plus 3x. It's a quadratic, obviously. Its graph opens up. It's got x-intercepts at -3 and 0. Got a vertical axis of symmetry at -3/2. I'm going to add a slidable point along this curve, and I'm going to label its coordinates. And I'm going to also add a tangent line. And so the slope of that tangent line can be interpreted as the instantaneous rate of change at that particular value. And you'll see the slope of that tangent line displayed off to the left in that little cell with the equal sign. So the slope of the tangent line to this curve at the point -3, 0 happens to be -3, happens to be the same as the x-coordinate, which is purely an accident. What we're going to do is take a look at the slopes of the tangent lines to this curve at various values of x and see if we can find some sort of pattern or some sort of regularity to the relationship between the x-coordinates and the slopes of the tangent lines. And this will sort of point us gently in the direction of the definition of the derivative. Here is a little table off to the side where we'll be recording our results. So at the point -3, 0, the instantaneous rate of change for that x, also known as the slope of the tangent line, is -3. And we'll just click through some of these, and we'll take integers because they're convenient. At the point -2, -2, the slope of the tangent line, as you'll see off to the left, is -1. At the point -1, -2, slope of the tangent line is 1. At the point 0, 0, slope of the tangent line is 3, and there seems to be some regularity emerging, but let's continue. At the point 1, 4, the slope of the tangent line is 5. At the point 2, 10, slope of the tangent line is 7. Anybody care to make a prediction about the slope of the tangent at x equals 3? Turns out it's 18. No, that's the y-coordinate. Turns out it's 9. At the point 428, it's 11. And let's do one more. At the point 540, the slope of the tangent line is 13. So if we had a less apparent pattern, we might want to do something like graph these instantaneous rates of change against these x's and try to see what such a graph might reveal. But as we look at this table, what we see is that as x advances by 1, the instantaneous rate of change advances by 2, which means the relationship is linear. So the instantaneous rate of change is linear with a slope of 2, so it's 2x plus something. And what's the something? Well, we happen to have the y-intercept staring us in the face down here. When x is 0, the slope of the tangent, instantaneous rate of change, is 3. So these instantaneous rates of change are 2 times the x-coordinate of the point plus 3. What we've done in effect is found a function that will save us the trouble of always having to recalculate the instantaneous rate of change of the function f of x equals x cubed plus 3x every time we want to know what it might be at a different value of x. And this function is going to have a name. It's going to be called the derivative. And that is the purpose of derivatives. They are designed to tell us for some function, instantaneous rates of change of that function at any value we choose to plug in, or equivalently, slopes of tangent lines, the graphs of that function, at any value of x that we choose to plug in. You'll see on your screen the formal definition of the derivative and a graph that sort of locates everything and orients it to the fact that we're still essentially taking limits of average rates of change in order to get at instantaneous rates of change. This will look very similar to the definition for the instantaneous rate of change at an individual point. The difference is we're not plugging in some numerical x naught and getting out some numerical value for an instantaneous rate of change. We're plugging in a generic x and getting out some function that will give us the instantaneous rate of change for any x we like. So formally, f prime is defined to be limit h to 0, f of x plus h minus f of x all over h, defined to be the derivative of f with respect to x. And the reason for that is that it's important to take note of what the independent variable is. And for those of you who ultimately take some multivariable calculus, there's going to be more than one independent variable, and then it becomes extremely crucial that we're clear about which one we're talking about. The domain, obviously, perhaps not obviously, but the domain can only be the set of all x's for which this limit exists. Limit doesn't exist, derivative doesn't exist, and so that value is not in the domain of the derivative. Our final task will be to verify that the derivative of f of x equals x cubed plus 3x is in fact 2x plus 3. And so I'll write down our function, f of x equals x squared plus 3x. And then as you saw in the formal definition, our notation, or a notation, for the derivative of some function f is f prime. And I'll write the definition first, and then we'll plug in the specifics that belong to this function. This is the limit h tiny of f of x plus h minus f of x all over h. And in our case, that is the limit h tiny of, what's our f? It's x squared plus 3x. So f of x plus h is x plus h quantity squared plus 3 quantity x plus h. Then minus f of x, which is x squared plus 3x all over h. This is a limit of the form 0 over 0. And we know that because we're talking about one point approaching closer and closer to another on the graph of a function. So as the x coordinates get closer to one another, their difference heads to 0. Same thing for the y coordinates, assuming that this derivative exists at this particular, or at a given location. And so this will be a situation where we'll have to do some algebra and hope that we can get out of the 0 over 0 position. So I'll expand everything. This is x squared plus 2hx plus h squared plus 3x plus 3h minus x squared minus 3x all over h. And some terms add to 0. So we can get them out of our way and see if that does us any good. And the answer is that it does, because everything that remains at this point has an h in it. So we'll just divide. I pull an h out of 2hx, I have 2x. I pull one out of h squared, I have h. I pull one out of 3h, I have 3. But then, as h approaches 0, what's this going to approach? 2x plus 3, and we did it. Now, you wouldn't necessarily be happy in a world where every time you wanted to know the derivative of a function, you had to start from first principles. plug into the definition and try to find some way of evaluating the resulting limit. Fortunately, there are rules that you will learn about in the future if you are just starting out your journey with differentiation or finding derivatives. That's another term for finding derivatives, differentiation. Um, there are rules for what happens when you add two functions, subtract them, multiply them, divide them, compose them. There are formulas for particular functions like the trig functions and exponential and log functions and so on. So you won't have to constantly be doing this. But this is really a good place to start if you want to have some conceptual understanding. Just for the record, there are other notations for derivatives, and here's one of them that you see fairly commonly, and that is this d dx notation. You stick it in front of your function, and that is understood to mean derivative with respect to x of this thing, which, as we said, was 2x plus 3. Or you might say y equals x squared plus 3x. And then dy dx, derivative of y with respect to x, is 2x plus 3. There are other notations that you don't see very often. These are the more common ones. I hope this has been a good sort of conceptual level introduction to what a derivative is and a little bit of testing of the waters of how you use the formal definition to evaluate a derivative. Happy mathing.